Hello everyone. Today we're going to enter the field of general topology. The book we'll be using for this matter is Analysis Now by Peterson, which is an excellent treatment on the subject, although not a quite complete one, but it's still very nicely written. The first thing we're going to talk about is the very interesting the Axiom of Choice and its equivalence. And why this is important? Actually, from historical perspective, this is something that is quite important that basically construct what we know as the modern set theory, or even, let's say, mathematical logic. And why it is so important? Actually, the axiom of choice is a kind of simple statement, but has some profound influence on quite a lot of things. First of all is this Zhang's lemma that we are going to introduce, and there are actually quite a lot of statements which are equivalent, by the way, about these same theorems or lemma or principle, but they turn out that the important thing here is that first of all these three things are both equivalent. So basically mean they are all axiom, and if you know one you can actually use the other one. And secondly, the more important thing is actually we are going to use this Cantor's well-ordering principle, or whatever you want to call it, as a so-called transfinite induction. So why we want to use so what do you mean by induction, you may ask? Well, if we remember that induction, mathematical induction, we have been focusing on, for example, basically the finite case. For example, we show that if we have something hold for n, and then it also holds for n plus 1, then we can show that up to a constant n which is smaller than infinity, something holds. And one might be interested in, for example, say, preserve this method of proving into a scenario of, say, a infinite dimensional, or the infinite cases. For example, if you have a function that is defined on, say, a certain closed interval, let's say, and you want to extend it to the whole R, it is not going to be that I can extend it 1 point each time and we still have a finite step of induction. We're going to have a infinite and uncountable many steps of induction. And it certainly doesn't really work if this is always applied. So you can actually come up with some quite interesting contradictories if you say that, okay, I can always do this. But here is what it makes it tick. So this is the thing that I assume to make this transfinite induction work. So let's start. Basically, the first thing here is a relationship, which you can imagine as smaller or equal than, that's the thing. We're not going to talk about the what is true or not. This doesn't matter. And then this order, we usually say it satisfies three properties. First is transitive, so x smaller or equal to y and y is smaller or equal than z implies that x is smaller or equal than z. Reflexive, which is x is always smaller than itself. And antisymmetric, so basically if x is smaller or equal than y and y is smaller or equal than x, it implies that x equal to y. And we can put a set and a order into a order set. So let's say an element x is called the majorant for a subset y of x if y is smaller than x for every y in y. So basically it says x is the largest element, but doesn't have to be unique. And so an order is filtering upward if every pair actually has a majorant, and then you can define same thing, and then we can also define like the lattice thing. This is basically the larger element. This is the okay, so this is the reverse. I just saw. Usually this is the larger element, this is smaller element, and we say that this is the important part, that this is a totally ordered set if either x smaller or equal to y or y smaller or equal than x. So this is actually interesting because usually if we think about real numbers, it's actually totally ordered. But if we go a little bit more difficult, let's say we are in R2, then we do not have a total order. Let's say if we have, in generally, let's say x smaller than y in R2, if both of the coordinate actually satisfy this relationship, then we have the 2 points that are not comparable. Now this happens for a lot of other things, but this also, we'll see that is actually very important. And finally, to say this x and this order set is well ordered if every non-empty subset of y has the smallest element, which is very interesting. So basically this says if this set is well ordered, then we have a largest element. So why this is actually very important. So first of all, here it uses the term smallest, but usually it is formulated as the largest element. Let's say if we consider a partial order, which is here. It's called an order, but usually it's called a partial order. Here that we have something like, let's say, a function f is smaller or equal to g if and only if, so first of all, the domain on which the function defined, the domain of f is contained in g. And also, let's say, you can add something else. For example, if on the same set they are defined, f and g must take the same value. Basically, we are going back to this functional extension thing. And then if we can show that it's well ordered, then basically in some way we can define the largest function that is basically defined on the whole R. Recall that we have just to define this function on the real interval from 0 to 1. So that's quite useful. And so it doesn't really work in general without any assumption. So the assumption here, which is useful, is this axiom of choice, which states that there is for each non-empty set X a choice function that maps this. Basically, this set is a power set, which maps it to X. What it says is basically if you give me a subset which is non-empty, then we can find a function basically which maps this non-empty set to a point that belongs to this set. So basically, why it's called axiom of choice. If you have a set, you can choose a point. That's more or less the thing that is assumed here. So why this is important? This seems pretty weak. That is why most mathematicians actually accept this axiom. But it actually there is this very nice equivalent which says that every set X has an order, such that this order set is well ordered. Basically, it has a largest or smallest element. And then there is also this Zhang's lemma, which says that every inductively ordered set, which means that if each total ordered subset of X has a majority in X and has a maximal element, which is quite nice, because basically what it says here is if you have this thing, then you can actually go to this well-ordering principle and then you prove something. So this is how it works usually in transfinite induction, that you show that actually if you can create an order that is basically totally ordered, so basically you can assume that this set is totally ordered, basically means and every two elements can be compared to each other. Then you can show that there exists basically in the largest element, which is the thing there. Well, that's pretty interesting, and we're not going to go over this proof. This proof basically says these three are equivalent, and this proof is actually not really the first proof that was given. First proof we can find is basically based on Bourbaki's fixed point theorem, which is something else. We're not going over this proof, but even if this seemed very short, it's actually pretty difficult proof, because it's very difficult to come up with this proof. And if one is interested in this, then we can actually use this exercise where this is the exercise. Basically says, well, we can have this function which is defined in this way, and then we can actually by using this thing, and then we have the whole function defined on R. That's the whole idea of this transfinite induction. So thank you very much. We are going pretty fast this time, so next time we're going to talk about the definition of topology. Until then, take care. Bye bye.